Hello everyone, welcome to the fifth episode of the series. In this video, we'll talk about vectors, matrices, and matrix arithmetic. So a vector is a column of numbers surrounded by brackets. For example, uh, the vector 2, 3, 4, we have a vector 0, 0, 0, 0. We have a vector of length 1, which is, just this minus 3, and so on. So here are some of the things that you need to know. So the entries are called coordinates sometimes, and by entries I mean the numbers that you actually put in the vectors. The size of a vector is the number of entries. So the first vector here is of size 3. This is a vector of size 4, size 1, and then size 4 again. And sometimes we call them like a 3 vector, a 4 vector, a 1 vector, and a 4 vector. So if we have a vector of size n, we call it an n vector. And we sometimes call these column vectors as well, just so we can distinguish them from row vectors. And a row vector is essentially when you write all of these, horizontally. So why do we need vectors? The purpose of vectors is to collect related numbers together and work with them as a single object. Let's look at an example. For any particular location, we can assign a latitude and a longitude degree to it. And the fun thing about latitudes and longitudes is that if you have both the numbers, you can precisely tell what location we are talking about on Earth. So we can combine these two quantities to write a single vector, and now this vector tells us the geographical location of the place corresponding to these latitude and longitude values. Here's another example. So if we have a linear system, its solution can be written down as a vector as well. So let's say if we have a solution to a linear system, which is x equal to 3, y equal to 0, and z equal to -1, we can write that as a column vector where our entries are 3, 0, and -1. Now, a very related concept to vectors is that of a matrix. Now, a matrix is a rectangular grid of numbers surrounded by brackets. These are some of the examples of matrices. And here are some of the things that you need to know. Now, the individual numbers, just like vectors, are called entries of a matrix here. The height of a matrix is the number of rows, and the width of a matrix is the number of columns. So this first matrix here has height 3 and width 3 because it has 3 rows and columns. This one here has height 1 and width 3 because it has 1 row and 3 columns. And this one here has width 4 and height 2 because it has 4 columns and 2 rows. And if you have a matrix of height m and width n, you call it an m by n matrix. Remember that we always write the height first. In other words, the number of rows first. So this square matrix is a 3 by 3 matrix. This is a 2 by 4 matrix, and this is a 1 by 3, and this is a 3 by 1 matrix. So I use the word square matrices. So we call a matrix a square matrix when the number of rows and columns is the same. So why do we need matrices? There's essentially two distinct purposes. The first is to collect tables of related numbers together, something similar to what I said about vectors a few moments ago. And the other is to describe linear transformations between vector spaces. And this is essentially just foreshadowing to more advanced stuff that we'll be learning in this semester. And as of now, you should forget about this second thing. And here's an example for a matrix, very similar to the latitude longitude example um, that we saw a moment ago. So here are some locations on campus, and you can find their latitude and longitude values, and you can store them together in a single matrix. So here's a fun fact. Every n vector, or a vector of length n can be treated as an n by 1 matrix. For example, this vector 2, 3, 4 is a vector of length 3 and can be treated as a 3 by 1 matrix because it has 3 rows and 1 column. And now we're going to move to doing some arithmetic on vectors and matrices. So the simplest operation is that of addition. So if you have two matrices of the same size, that is they have the same height and the same width, then we can add the two matrices by adding respective entries together. For example, if I have these two matrices of exactly the same size, so both of these matrices have 2 rows and 4 columns. So we essentially add entries together that are on the same position in the matrix. So this 1 will get added with this 1 and leave a 2. 2 will get added to this 3 and leave a 5. 8 will get added to 0 and leave a 8. So the sum of two matrices of different sizes does not make sense at all. For example, we cannot add these two matrices to each other because there is no well-defined way to do so. Another operation I want to talk about is of scalar multiplication. So if A is a matrix and R is a number, then R times A is the matrix where you multiply each entry of A by R. For example, if you have this 2 by 4 matrix and you multiply it with the scalar 2, then you're essentially multiplying every single entry on the inside by 2. So scalar is just a fancy word for number, and we use the word scalar multiplication to distinguish from matrix multiplication, which we'll see perhaps in the next episode. One of the other properties that scalar multiplication satisfies is that it can be distributed over addition. In other words, R times A plus B is the same as R times A plus R times B. So the third thing I want to talk about is a concept that is related to both addition and scalar multiplication, and that's the linear combination of matrices. So if we have n matrices A1, A2 through AN of the same size, and if R1, R2 through Rn are numbers, then any expression of this form, R1, A1 plus R2, A2 plus dot 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 Rn, AN is a linear combination of these matrices. For example, if we have these three vectors 1, 0, minus 1, 0, 2, 3, 1, minus 2, 3, then 2 times this first vector, 1 times this second vector, and minus 2 times this third vector is 0, 6, minus 5. So what we say is that 0, 6, minus 5 is a linear combination of 1, 0, minus 1, 0, 2, 3, and 1, minus 2, 3. Okay, let's look at an exercise. So we are given this linear system in 3 variables, and we want to write it as a combination of vectors. So the way you can do that is you multiply each variable by the vector of coefficients corresponding to that variable. So in other words, the first vector will correspond to just the coefficients of x1. So the coefficients of x1 are 3, 1, and 0 because there's no term in the last equation. So you make a vector 3, 1, and 0, and you multiply it to the variable whose coefficients that we're working with. Similarly, we have 2, minus 3, and 1 for x2. So we make a vector of the coefficients and we multiply it with x2. Then we have minus 4, 1, and minus 5. We make a vector out of these and we multiply it with the variable x3. And in the end, we have 0, 3, and minus 1. These are constant terms. So we put a put them in a vector form, and we leave them as is. So the last thing I want to talk about is this operation of a transpose. So if I have an m by n matrix A, its transpose A to the T is the n by m matrix which reflects along the main diagonal. In other words, the transpose exchanges the rows and the columns. Uh, let's see an example. So if we have this 2 by 4 matrix here, and we want to take its transpose, what we end up doing is we take all the rows and we convert them into columns and then restack them together. So I take this row vector 1 3 minus 1 minus 3, convert it into a column 1 3 minus 1 minus 3, and then I go to the second row 0 1 0 minus 1 minus 2 0, and I write it as a column again. Similarly, if I have 1 minus 2 3, this is a 1 by 3 matrix, and if you take its transpose, you end up getting a 3 by 1 matrix. So I want to talk about the properties of the transpose. So the first property is that of distributivity. So in other words, A plus B transpose is the same as A transpose plus B transpose. R times A transpose is the same as R times A transpose. In other words, if you want to take the transpose of a matrix R times A, where R is a scalar multiplied to a matrix A, it's the same as first taking the transpose of A and then multiplying it with the scalar R. And most importantly, if you have a matrix A and if you take its transpose twice, you get your original matrix back. And I would like to finish this with an exercise. So we're given these 4 matrices, and we just want to write their transposes, and it's not very difficult. So for example, for A, we have a 3 by 1 matrix. So we first take this 1 because that's the only element present in the first row, and we write it as a column, so we get like a very short column, of height 1. Similarly, we put 3 here, and then we put 2. When we're trying to take transpose of B, we end up converting this 1 by 3 matrix into a 3 by 1 matrix. For C, we take this first row 1 2, and it becomes the column 1 2. The row 3 4 becomes the column 3 4, and the row with entries 5 6 becomes a column with entries 5 6. So we've converted this 3 by 2 matrix into a 2 by 3 matrix, and similarly we can work with D. And you would find out that D is the same as D transpose, and that's true because if you draw a line along the diagonal, then the entries are symmetric. There's a 1 and a 1, there's a -1 and a -1, and there's a 2 and a 2. And with this, I would like to end this episode. I will see you guys in the next episode. Until then, happy learning.